Okay, my friends. As you can tell, I am super sick. That's why I was out yesterday. But I only want to have to explain this once because I think that might be all I have in me. And so let's follow along. You should have all of the same numbers I do. And instead of just watching this video, you should be interacting with it. So when I say pause the video, you need to pause the video. Make sure you get the same answer I do, and then keep going. So my rocket is 2.9 ounces, and we actually need to convert that to kilograms. And so since there's not a spot to do that on here, I'm literally just going to Google 2.9 ounces to kilograms. And oh my gosh, me trying to write on this. And I get 0.085. And so again, I just Googled that answer, and that's how I got that. Okay. These two bits of information right here, the impulse and the burn time, those are constants. So we're all going to have the same one. They're just characteristics of that C65 engine. The impulse is like the oomph. So it's how much momentum it has. The burn time, I actually thought this is what the 5 was, the 5, but it's not. The 5 is just the number of seconds before the parachute comes out. So burn time, this engine burns for 1.6 seconds. So to find our thrust, which is our first one we want to find, what we're going to do is we're going to do the impulse divided by time. Since we all have the same impulse and we all have the same time, this will be the same for everyone. So our impulse, as shown above, is 10 Newton seconds divided by our time, which is 1.6 seconds. Okay, pause the video here and check your answer. We get, our seconds cancel out, we get 6.25 newtons. And let's go ahead and round to the nearest hundredth for all of these. And all we're going to do is we're going to keep using these down, so just be careful. And now we need to find the force of gravity. So the force of thrust is what was pushing us up. Force of gravity is how much pull down do we have, and this depends a lot on your weight. So again, we're all going to do mine for this first time, and then the second time through you can do your own. So we're all following the same math together. So my weight was 0.085 kilograms times, we all have the same gravitational constant because we're all on Earth doing this. If you were on Mars doing this, I would have you put in some different numbers, but you are most likely not. Okay, go ahead and give that equation a try. Pause it right here and see what answer you get. I got 0.83 newtons. So we're pushing up with 6.25 newtons, pulling down with 0.83 newtons. To find our net force, all we need to do is subtract the two. 6.25 minus 0.83. Newtons minus newtons, so we should get newtons, and our answer is 5.42 newtons. So that's how much thrust, or how much force we have going up. Now let's figure out our acceleration. So we have our force net, our net force right there. If you notice, all we're really doing is plugging in numbers. Divided by our mass. Again, we're all sticking together on this. My mass was 0.085. That's what you should write down as well. And see what you get. I got 63.76 meters per second squared. So acceleration is like how fast it's speeding up. And so that is 63.76 meters per second squared. Oh, excuse me. So, G's. Acceleration is directly proportional to, if you've heard of G's, like when flight or in roller coasters, or G's is the amount of gravity that you experience. So you're always experiencing one gravity. But acceleration can make it feel like, or actually make you experience more gravity. So all we need to do is our net acceleration, which we found was 63.76 meters per second squared. We're going to divide that by our gravitational constant, which is 9.8 meters per second squared. Notice we divided 2 meters per second squared, so we're just getting a ratio. Go ahead and give that number a try. .51 G's. And so our eggstronaut, survived or didn't survive 6.51 G's. An average astronaut is anywhere from 3 to 6 G's. And sometimes can go up to 9 G's with training. That's just a little side note, though. No, I'm recording a video. Yeah, you're good. That's okay. That was just Mr. Smith. Austin, is it important?
Here's a pre-signed checkout list.
Thank you. Thanks.
Sorry.
You're good. Okay, back to work. Okay, so now we need to figure out our velocity afterburn, because this rocket launch happened in 2 phases. So let's draw a little picture over here. So we're on the ground, right here, and our engine burns for 1.6 seconds, right? And so that's our burn phase. Burn. And that's how we're accelerating that whole time. And so this is really the fastest point. Right here is the fastest that we will be. And so we want to see our speed. Velocity is just kind of another word for speed. Our speed at that point, because that is the fastest point we will be going. So our initial velocity is our net acceleration. We've already figured that out. And we need to times that by our time, because that's how long we'll be accelerating that much. Again, 1.6 seconds. So go ahead and give that a try. Should have gotten 102.02 meters per second. So every second, at that point, your rocket's going 102 meters. At least mine was, hypothetically. And now we need to figure out the height at that point. Because we have the speed, we need to figure out the height. Here's our equation for velocity initial, but we're actually going to switch that around a little bit so we can solve for the height after burn. So if we divide by this, we can get the height after burn by itself. Uh-oh, did I change it to green? I don't want green. Okay, let's see if I fixed it. We divide this side by 2a net. Well, I changed it, but life will go on. And so we get that the height after burn is going to be velocity initial squared. Don't forget that square, that's important. Over 2 times our a net. So now we look. What was our velocity initial? It was 102.02. We're going to square that. Divided by 2. Put these in parentheses when you do this, because if not, you'll be dividing by things. Times our acceleration net, 63.76. Definitely give this one a try before you check my answer, because a lot of people mess up on this one. So pause it right here, give this a try, and make sure you get what I get. Okay, I got 81.62 meters. So at this point, I was at 81.62. If you got a crazy big or crazy small number, remember this is about how high we are after 1.6 seconds, so it has to make sense too. Now we enter what's called the free fall phase or the coast phase, because it doesn't just stop right there, right? It's still moving. And so it's still on an upward trajectory. And so same thing, we're going to divide by -2 gravity. Whoa. On both sides. So we get something that looks like h of free fall, height of free fall, equals 102.02 squared divided by, we're timesing -2 because that's the equation, times -9.8. And the reason we're doing that is 9.8 is our gravitational constant, but we don't want a negative number here. So we just made that negative. We could have absolute valued it too. 19.6. Pause this again and make sure you've got the right answer. I got 531.02 meters. So what that means is that this height was 531.02 meters. So all we need to do now is add them together. So we've got our maximum height, 81.62, plus 531.02. And my theoretical, without air resistance, that's a huge thing. This won't look anything like your actual number. 612.64 meters. This might look closer. I picked a number really low, so mine's way higher than yours. This might look closer to your SpaceCAD number. You are welcome to ask me questions about this, but not about your own math, since that is a summative. So there you go.